Hey. So, before we start, I want to give you one number. Just one. And if this number does not change something about the way you think about Earth, then I have done something wrong in this video. The number is 0.001. That is the percentage of the deep ocean floor that humans have directly seen. Not explored. Not mapped from orbit. Directly seen, with a camera, a submersible, or human eyes. 0.001%. To put that into physical terms, that is roughly the area of Rhode Island, one small American state, on a planet that is 70% ocean. We have sent humans to the moon. We have landed robots on Mars. We have photographed galaxies 13 billion light years away. And we have directly seen less of our own ocean floor than would fit inside the smallest state in the country. That number is from NOAA, the National Oceanic and Atmospheric Administration. Not a guess. Not an estimate from a blog. The agency responsible for studying the ocean says we have barely looked at it. And here is the thing that makes this worse. The average depth of the ocean is 3,782 meters. That is over 2 miles straight down. Most of that, the vast majority of it, exists in permanent darkness, at pressures that would crush a submarine, at temperatures near freezing, with no sunlight and almost no food falling from above. It is, by any reasonable definition, the most alien environment on this planet, and it covers more surface area than every continent combined. This video is a descent. We are going to start at the surface and go straight down, layer by layer, zone by zone, all the way to the bottom of the deepest trench on Earth. And at every level, I am going to show you what lives there, what we have found there, and what we still do not understand. Some of it is beautiful, some of it is genuinely unsettling, and some of it is so strange that if you described it to someone without context, they would assume you were making it up. If you stay for this, and it is a long one, I will not lie about that. Subscribe. Because MindSnap exists to find facts that change how you see everything. And this one, what is actually beneath the water you swim in, sail on, and take completely for granted. This one changes a lot. Let us begin at the surface and go down. The first layer is the one you know. The one you have swum in, or at least seen photographs of. Warm, bright, full of color. It is called the epipelagic zone, but most people just call it the sunlight zone. It extends from the surface down to about 200 meters. That is roughly 660 feet. The depth of a 60-story building if you turned it upside down and sank it. This is where almost everything you associate with the ocean lives. Coral reefs, dolphins, tuna, sharks, sea turtles, whales at the surface, breathing, seabirds diving, plankton blooming in vast green clouds visible from space. And that last one, the plankton, is worth pausing on, because it does something that most people have no idea about. Phytoplankton, microscopic plant-like organisms floating in the sunlight zone, produce roughly half of all the oxygen on Earth. Not a third, not a quarter. Half. Every second breath you take exists because of organisms too small to see, floating in the top layer of the ocean. They do this through photosynthesis, the same process trees use. Sunlight, carbon dioxide, water. But trees get all the credit. Nobody plants a phytoplankton. Nobody campaigns to save them, and yet remove them. And the atmosphere changes in ways that would end most life on land within decades. This is the zone where sunlight penetrates, and sunlight means photosynthesis. And photosynthesis means food, a base layer of energy that everything above it depends on. The entire ocean food chain starts here, in the top sliver, the top 5% of the water column, which means everything below this, everything we are about to descend into, lives without that energy source. No sunlight, no photosynthesis, no plants, just darkness, and whatever manages to survive in it. Now, 200 meters does not sound like much, and for the ocean, it is not. But here is what changes at that boundary. At 200 meters, roughly 99% of sunlight has been absorbed. What remains is a faint blue-gray glow, enough for some eyes to detect, not enough for any plant to use. The water temperature drops. The pressure has already increased to about 20 times atmospheric. And the abundance of life, the sheer density of living things per cubic meter, begins to fall off sharply. You are about to enter a world that most humans will never see. And it starts with a color change. The water turns from blue to dark blue, then from dark blue to black. The mesopelagic zone, the twilight zone, 200 meters to 1,000 meters. And this is where the ocean stops being familiar and starts being something else entirely. The first thing you notice, or rather, the first thing a submersible pilot notices, is that the light does not disappear all at once. It fades. Slowly, the blue gets deeper, darker, heavier. At 300 meters, you can still see your hand if you hold it against the viewport. At 500 meters, you cannot. At 800 meters, the only light in the universe is whatever you brought with you. And yet, this zone is not empty. It is, in fact, one of the most densely populated layers of the ocean. It just does not look that way during the day, because the residents are hiding. During daylight hours, the creatures of the twilight zone sink deep, staying below the reach of predators that hunt by sight. Then, every single night, as the sun sets and the surface darkens, they rise. Billions upon billions of fish, squid, shrimp, jellyfish, and organisms we do not even have common names for, all ascending hundreds of meters toward the surface to feed on plankton under cover of darkness. This is called the Deal Vertical Migration, and it is the largest migration of living things on Earth. Not the largest in the ocean, the largest on Earth. Larger than the wildebeest migration, larger than any bird migration, larger than anything that happens on land. Every single night, a living layer of the ocean moves upward through hundreds of meters of water. Every single morning, it sinks back down. The biomass involved is staggering. Estimates vary, but the twilight zone may contain more fish, by weight, than the rest of the ocean combined. And we discovered this relatively recently. For most of human history, we had no idea this migration was happening. Think about that for a moment. The largest movement of life on the planet, happening every night. And we did not know about it until sonar started picking up a mysterious layer that rose and fell with the sun. During World War II, naval sonar operators noticed something strange. There appeared to be a false bottom to the ocean, a solid-seeming layer that reflected sonar sitting a few hundred meters below the surface. They called it the deep scattering layer. It confused submarine crews because it looked like the seafloor, but it was in the wrong place. And it moved. It took years before scientists worked out what it was. Not a geological feature, not an instrument error, a living wall of organisms, so dense it reflected sound. That is what lives in the twilight zone, a wall of life thick enough to fool sonar. And among that wall, some of the strangest animals on the planet. The hatchetfish, a small, flat silver fish with enormous upward-pointing eyes. It lives in the twilight zone and does something remarkably clever. On its underside, it has rows of light-producing organs called photophores. These organs produce light that matches the color and intensity of the faint sunlight filtering down from above. Why? Because if a predator is looking upward from below, the hatchetfish would normally appear as a dark silhouette against the dim glow. The photophores eliminate that silhouette. The fish becomes invisible from below. It is called counter-illumination. And it is one of the most elegant camouflage strategies in biology. Then, there is the glass squid. Entirely transparent except for its eyes and a small digestive gland, you can see through its body. The only visible part of it is the food it has recently eaten, which appears as a small dark spot floating inside what looks like a ghost, and the siphonophores. These are not individual animals, they are colonies. Chains of specialized organisms linked together into a single functioning body that can stretch tens of meters long. Some produce bioluminescent light, some trail stinging tentacles. Some are responsible for propulsion. Together they form something that looks like a single creature but is actually hundreds of cooperating individuals. The twilight zone is a factory of evolutionary solutions to a problem most land animals never face. How do you survive in a world where you can barely see, where the pressure is crushing, where the food is above you during the day and you cannot reach it without being eaten, and where the only light available is the light you make yourself? The answer, apparently, is that you become something humans would not have believed existed if they had not gone down and looked. And we are only at 1,000 meters. Below 1,000 meters, the twilight ends. The bathypelagic zone. The midnight zone. 1,000 to 4,000 meters. And the name is not poetic. It is literal. There is no sunlight here. None. Not a photon of solar origin reaches this depth. The darkness is absolute. The kind of darkness that a human being living on the surface of the earth never experiences. Not a dark room. Not a moonless night. Absolute zero light. The temperature hovers between 1 and 4 degrees Celsius, just above freezing, and it stays there, year-round, century after century. There are no seasons in the midnight zone, no weather, no day and night, just cold, dark, pressurized water, everywhere, all the time. The pressure at 2,000 meters is roughly 200 times atmospheric. At 4,000 meters, it is 400 times. A styrofoam cup lowered to this depth on a string comes back the size of a thimble, crushed uniformly by pressure from every direction. And the food supply is almost nothing. Everything that lives in the midnight zone depends on what falls from above. Dead plankton, fecal pellets, the occasional carcass of a larger animal. Scientists call this marine snow. A constant, slow, silent rain of organic particles drifting down through the water column. Marine snow. It sounds gentle. It is, in a sense, the only connection between the sunlit world and the deep. A thin, unreliable thread of nutrition that gets thinner with every meter of depth. By the time it reaches the midnight zone, most of it has already been consumed by the animals in the twilight zone above. What arrives is scraps, fragments, barely enough to sustain life. And yet life is here. The anglerfish. You have probably seen pictures. A bulbous, dark, grotesque fish with a bioluminescent lure dangling from its forehead. It sits in the darkness, motionless, burning almost no energy, waiting for something to be attracted to the glow. But the part most people do not know is how it reproduces. Finding a mate in the midnight zone is an almost impossible problem. The density of life is so low that 2 anglerfish of the same species encountering each other in the dark is a near miraculous event. So the males do something radical. When a male anglerfish finds a female, he bites into her skin and does not let go. Over time, his body fuses with hers. His circulatory system merges with hers. His organs degenerate. His eyes dissolve. He becomes essentially a permanently attached reproductive organ. A parasite that was once a fish. Some females have been found with multiple males fused to their bodies, all reduced to nothing but pouches of sperm, fed by her blood, attached permanently. That is what the midnight zone does to biology. The conditions are so extreme that evolution produces solutions that sound like horror fiction. Then, there are the giant squid. For centuries, they were mythology, sea monsters, kraken. No scientist had ever seen one alive in its natural habitat until 2012, when a team led by Tsunemi Kubodera filmed one at roughly 900 meters near the upper boundary of the Midnight Zone in the Pacific Ocean south of Japan. The footage lasted about 3 minutes. The animal was estimated at around 3 to 4 meters in body length, with tentacles bringing the total to perhaps 8 meters. The giant squid has the largest eyes of any living animal, up to 27 centimeters in diameter, roughly the size of a dinner plate. In a world of total darkness, why would any creature evolve such enormous eyes? The leading theory is that they are not looking for light. They are looking for bioluminescence, the faint glowing trails left by smaller organisms disturbed by the approach of a predator. Specifically, they may be watching for the bioluminescent wake of sperm whales, their only significant predator. Those enormous eyes are not searching for prey. They are watching for danger in the dark. At the bottom of this zone, around 4,000 meters, you reach the average depth of the ocean floor. Most of the seafloor on Earth sits at roughly this depth. If you were to drain all the water, the majority of the planet's solid surface would be a vast, flat, silty plain at about 4 kilometers depth, stretching in every direction. That plain is called the abyssal plain, and it is the largest habitat on Earth, larger than all the forests, larger than all the deserts, larger than all the grasslands and cities and mountains combined, and almost nobody has ever seen it. The abyssopelagic zone, 4,000 to 6,000 meters, and here is where the ocean does something unexpected. After the midnight zone, after the pressure, the darkness, the cold, the vanishing food supply, you might expect the abyss to be a wasteland, an empty, featureless expanse of mud. In some places, it is exactly that. Vast stretches of abyssal plain that look, on camera, like a gray desert. Sediment that has been accumulating for millions of years, particle by particle, layer by layer, made up of the shells of dead organisms, volcanic dust, and clay carried by ocean currents from continents thousands of kilometers away. In a single square centimeter of abyssal sediment, you can find material that took thousands of years to settle. The sedimentation rate is roughly 1 to 2 centimeters per 1,000 years. The mud you see on camera at 4,000 meters depth has been building since before human civilization existed. But the abyss is not empty, and what lives there challenges almost everything we thought we knew about what life requires. In 1977, and this is genuinely one of the most important discoveries in the history of biology, a research team aboard the submersible Alvin Dove to the Galapagos Rift, a volcanic spreading center on the floor of the Pacific Ocean. They were looking for hydrothermal vents, places where seawater seeps into the crust, gets superheated by magma, and blasts back out. They found the vents. But what shocked them was not the geology. It was the biology. Around the vents, in total darkness, at crushing pressure, in water that should have been sterile, there were ecosystems. Dense, thriving, complex ecosystems. Giant tube worms over a meter tall with bright red plumes anchored to the rock. Clouds of white shrimp. Mussels. Crabs. Entire communities of organisms living at densities comparable to a coral reef. And none of them depended on sunlight. This was the discovery that changed biology, because until that moment, every known ecosystem on Earth depended directly or indirectly on photosynthesis. Sunlight hits a plant. The plant makes sugar. Something eats the plant. Something eats the thing that ate the plant. Energy from the sun, all the way down. The vent communities had no access to sunlight. None. Their energy source was chemosynthesis. bacteria that extract energy from hydrogen sulfide and other chemicals pouring out of the vents. Those bacteria form the base of the food chain. The tube worms do not eat food. They have no mouths, no stomachs. They host the bacteria inside their bodies in a specialized organ called a trophosome, and the bacteria feed them from the inside. A symbiosis between a worm and a bacterium, powered by volcanic chemistry, in total darkness, at 400 times atmospheric pressure at the bottom of the ocean. If you had described this to a biologist in 1970, they would have said it was impossible. And then there are the black smokers. Hydrothermal vents that produce plumes of superheated water at temperatures exceeding 400 degrees Celsius, hotter than molten lead. The water does not boil because the pressure is so extreme that the boiling point is suppressed. It is liquid at 400 degrees. The plumes are black because they are loaded with dissolved metals, iron, copper, zinc, manganese, that precipitate out when the superheated water meets the near-freezing ocean. They build chimneys of solid mineral, sometimes 20 meters tall, belching black clouds into the dark. And around those chimneys, in water that is simultaneously near-freezing and lethally hot depending on which side you are on, animals live. They navigate the gradient. They know where the safe zone is. Some of them graze on bacterial mats just centimeters from water that would kill them instantly. Life, it turns out, does not need sunlight. It does not need a comfortable temperature. It does not even need a stable environment. It needs chemistry. And chemistry is everywhere. That single discovery, hydrothermal vent ecosystems, is one of the reasons astrobiologists now believe life could exist on the ocean floor of Jupiter's moon Europa or Saturn's moon Enceladus. If life can thrive at the bottom of our ocean without sunlight, powered by nothing but geology and chemistry, then it can, in principle, thrive anywhere those conditions exist. And they exist in a lot of places we used to assume were dead. Part 2. The descent continues. Here is something that still makes me uncomfortable when I think about it for too long. Life does not stop at the ocean floor. It goes further down, below the sediment, below the mud, into the rock itself. Scientists call it the deep biosphere, a vast, slow, ancient community of microorganisms living inside the Earth's crust, kilometers below the seafloor. These are not the colorful ecosystems of the hydrothermal vents. There are no tube worms, no shrimp, just bacteria and archaea wedged into cracks in basalt, surviving on chemical reactions so slow that a single cell division can take hundreds or even thousands of years. Read that again. A single cell division, thousands of years. On the surface, a bacterium like E. coli divides every 20 minutes. In the deep biosphere, the same fundamental process, one cell becoming two, can take longer than the Roman Empire lasted. These organisms are alive, but they exist on a timescale so different from ours that calling them alive almost feels like a different use of the word. The Ocean Drilling Program and its successor, the International Ocean Discovery Program, have been pulling core samples from beneath the seafloor for decades, and in sample after sample, at depths that everyone expected to be sterile, they find cells, living cells, metabolizing, persisting. In 2020, researchers revived microorganisms from sediment cores beneath the South Pacific seafloor that were over 100 million years old. The sediment had been laid down during the age of dinosaurs. The organisms had been sitting there, not dead, not reproducing, not quite alive in any sense we would normally recognize, for 100 million years. And when given nutrients in a lab, they woke up. They started eating. They started dividing. That is not survival. That is something else. Something we do not have a good word for. A state between life and death that lasted longer than most species exist. The total biomass of the deep biosphere is difficult to estimate, but some calculations suggest it may rival the biomass of all life on the surface. All the forests, all the grasslands, all the animals, matched or exceeded by organisms living in rock beneath the ocean that nobody knew existed until a few decades ago. And this raises a question that astrobiologists take very seriously. If life can persist in rock, at enormous pressure, without sunlight, without oxygen, without any connection to the surface, for 100 million years, then what exactly rules out life inside Mars? Or inside the ice crust of Europa? Or in the subsurface of Enceladus? The answer, uncomfortably, is that nothing rules it out. And the deep biosphere is why. There is also a category of organism that lives in conditions so extreme that biologists had to invent a word for them: extremophiles. Organisms that thrive in environments that would kill virtually any other life form. There are thermophiles that live in water above 100 degrees Celsius, psychrophiles that thrive near the freezing point, barophiles that require crushing pressure to function, acidophiles that live in water more acidic than battery acid, halophiles that survive in salt concentrations that would pickle anything else. And at the bottom of the ocean, several of these categories overlap. An organism living near a black smoker might simultaneously be a thermophile, a barophile, and a chemolitho-autotroph. An organism that eats rock, essentially. It does not need organic food. It does not need sunlight. It gets its energy from chemical reactions between water and minerals. If you were designing life from scratch to survive in the most hostile environment imaginable, you would probably come up with something similar to what already exists at the bottom of the ocean. Evolution got there first, and it got there billions of years ago. Below 6,000 meters, the ocean enters its final zone, the one named after the underworld, the Hadal Zone. Named after Hades, the Greek god of the dead. 6,000 to 11,000 meters. And it exists almost entirely inside ocean trenches. Narrow, steep-walled gashes in the seafloor where one tectonic plate is being shoved beneath another. 46 Hadal habitats have been identified worldwide. Together they cover an area roughly half the size of Australia, and yet they represent less than 0.25% of the total ocean floor. These are tiny zones, geologically speaking, but they contain the most extreme conditions anywhere on the planet's surface. The pressure here ranges from 600 to over 1,000 times atmospheric. At the deepest point, the pressure is approximately 8 tons per square inch. That is roughly equivalent to 100 elephants standing on your head. Or if you prefer a different image, it is roughly equal to the weight of a large commercial aircraft concentrated on a single human body. Nothing built by humans can survive that pressure casually. Submersibles that reach full ocean depth are engineering marvels. Titanium spheres with walls thick enough to withstand forces that would crush a nuclear submarine. The Nereus, a robotic vehicle built by Woods Hole Oceanographic Institution, successfully reached the bottom of the Mariana Trench in 2009. In 2014, on a mission to the Kermadec Trench near New Zealand, it imploded. The pressure destroyed a purpose-built deep ocean vehicle. And yet life is here too. In 2014, scientists discovered a species of snailfish, a small, translucent, tadpole-like creature living at 8,178 meters in the Mariana Trench. It was, at the time, the deepest living fish ever recorded. That record has since been broken. In 2023, a snailfish was filmed at 8,336 meters in the Izu Ogasawara Trench, south of Japan. These fish are not what you expect. They are not armored, they are not monstrous. They are small, soft, almost delicate looking. Their bones are partially cartilaginous, less rigid, more flexible. Their cells contain high concentrations of a chemical called trimethylamine N-oxide, or TMAO, which stabilizes their proteins against the crushing pressure. Without TMAO, their enzymes would deform and stop working. Below the fish, amphipods take over. These are crustaceans, related to the sand fleas you might see on a beach, but adapted for the hadal zone. Some hadal amphipods grow to extraordinary sizes, 10 centimeters or more, compared to their shallow water relatives that are typically a few millimeters. This is called abyssal gigantism, and nobody fully understands why it happens. Cold water, high pressure, and limited food should, in theory, produce smaller organisms. Instead, some of them grow larger. The giant amphipods are scavengers. Drop a piece of bait to the bottom of a trench and within hours, sometimes within minutes, they arrive. Hundreds of them, swarming. In an environment where food almost never appears, the response to food is immediate and overwhelming. Where do they come from? How do they detect the food? The hadal zone is vast and the organisms are sparse. And yet they find a food fall faster than you would find a new restaurant. The sensory mechanisms involved are still not fully understood. Chemoreception, essentially smelling dissolved chemicals in the water, is the leading hypothesis. But the speed and precision of the response across kilometers of dark water remains one of the open questions of hadal biology. And then there is something even stranger. In 2020, China's Fenduze submersible, the name means striver, descended to the bottom of the Mariana Trench and filmed organisms that had never been seen before. New species, completely unknown to science, living at the very bottom of the deepest place on Earth. Every single time a submersible goes to the hadal zone, it finds something new, not occasionally. Every time. That is how little we know about this layer. And now we reach the bottom. Challenger Deep, the deepest known point on the surface of the Earth, located in the Mariana Trench in the western Pacific Ocean, roughly 300 kilometers southwest of Guam. The depth is 10,984 meters, nearly 11 kilometers straight down. If you placed Mount Everest at the bottom of Challenger Deep, its peak would still be more than 2 kilometers below the surface of the ocean. The pressure here is 1,086 times atmospheric. Every square centimeter of surface is pressed by a force equivalent to roughly 1,100 kilograms. The temperature is between 1 and 4 degrees Celsius. There is no light. There has never been light here. Not once. Not in the entire history of this planet. And more people have walked on the moon than have been to the bottom of Challenger Deep. As of 2026, 12 humans have walked on the lunar surface during the Apollo program. The total number of people who have reached the bottom of Challenger Deep, in any vehicle for any duration, is roughly 27. Some counts vary depending on whether you include all occupants of multi-person dives. But the number is in that range. The deepest point on our own planet has been visited by fewer people than the surface of the moon, which is 384,000 kilometers away. What did they find down there? The first thing every account mentions is the sediment, a thick layer of pale, fine-grained material covering the bottom. It looks like snow. In some descriptions, it looks like the surface of the moon, flat, pale, and utterly featureless to the horizon. But it is not featureless to instruments. Acoustic surveys have mapped the topography of Challenger Deep in detail, and it is not flat. There are ridges, slopes, and smaller depressions within the trench. The bottom is not a single point, but a long, narrow valley, roughly 5 kilometers wide and about 10 kilometers long, at the base of walls that rise more than 10 kilometers on either side. The sediment itself is largely composed of the accumulated shells of foraminifera, single-celled organisms that live in the upper ocean, die, and sink. Over millions of years, their shells build up into a thick layer of calcareous ooze. Except that at Challenger Deep, the depth is below the carbonate compensation depth, the point at which calcium carbonate dissolves faster than it accumulates. So the sediment composition is different here, more siliceous, more clay. A record of what dissolved on the way down, as well as what survived. And in that sediment in the deepest, most pressurized, most isolated environment on the surface of the Earth, there are organisms, foraminifera. Single-celled organisms with shells made of organic material rather than calcium carbonate, since carbonate dissolves at this depth. They are alive. They are functioning. They are reproducing, slowly, in conditions that would destroy virtually any other multicellular organism. Bacteria were found in the water and the sediment. Amphipods have been filmed at or near the bottom. And in several expeditions, researchers have found something that should not be there at all. Plastic. Microplastics have been detected in sediment samples from Challenger Deep. A plastic bag was filmed at the bottom of the Mariana Trench. In 2019, Victor Vescovo, who at that point had just completed the first descent to the deepest point in every ocean, reported seeing what appeared to be a sweet wrapper at the bottom. The deepest, most remote, most inaccessible place on the surface of the Earth. And human refuse got there before most humans did. That fact does not need commentary. It speaks for itself. The history of human descents to Challenger Deep is short, and every one of them is worth knowing because each tells you something different about why we explore and what it costs. The first was January 23, 1960, the bathyscaphe Trieste, piloted by Don Walsh of the US Navy and Jacques Picard, a Swiss engineer. The descent took nearly 5 hours. The ascent took about 3 hours and 15 minutes. They spent roughly 20 minutes at the bottom. Trieste was not a submarine in any normal sense. It was a hollow steel sphere, the crew compartment, hanging beneath a giant float filled with gasoline, which is lighter than water and provided buoyancy. Iron shot pellets served as ballast. To descend, you did nothing. The weight pulled you down. To ascend, you released the iron shot, and the gasoline float brought you back up. There was no propulsion, no way to move laterally. You went straight down and straight back up. If anything went wrong, there was no rescue. No one could reach you. Not in 1960. During the descent at roughly 9,000 meters, the outer plexiglass window on the entrance tunnel cracked. Walsh and Picard heard the sound. They continued descending. They had no way of knowing whether the crack would hold or propagate. It held. At the bottom, they looked through the tiny viewport and saw the sediment cloud stirred up by their landing. And as it cleared, Picard later reported seeing what he described as a flatfish. A sole, he thought, lying on the bottom. That observation was controversial for years. Many biologists doubted that a bony fish could survive at that depth. The observation has never been definitively confirmed, but it was never disproven either. After 20 minutes, they dropped their ballast and began the ascent. They surfaced safely. Nobody went back for 52 years. On March 26, 2012, James Cameron, the filmmaker, director of Titanic and Avatar, piloted the deep-sea Challenger to the bottom of Challenger Deep. Solo. He was the third person ever to reach the bottom and the first to do it alone. Cameron spent approximately 3 hours at the bottom, collecting samples and filming with custom-built 3D cameras. He described the landscape as a very lunar, very desolate place, isolated. My feeling was one of complete isolation from all of humanity. The submersible worked, but Cameron later said that a hydraulic leak limited the functionality of his sampling arm and that he wished he could have stayed longer. The footage he captured was used in a National Geographic documentary. Then, in April and May 2019, Victor Vescovo completed multiple dives to Challenger Deep as part of his 5 Deeps expedition, the first project to reach the deepest point in all 5 of the world's oceans. Vescovo made 4 dives to the bottom of Challenger Deep in his submersible limiting factor. On one dive, he reached 10,928 meters, at the time the deepest crewed descent ever measured. Vescovo is not a scientist. He is a private equity investor, a retired naval intelligence officer, and an explorer. He funded the project himself. The submersible was built by a company called Triton, and it is one of only 2 vehicles in the world certified for repeated full ocean depth dives. Since Vescovo, China has sent its Fenduji submersible to the bottom, and commercial dive operations are now in the early stages of planning regular access to Challenger Deep for scientists and eventually tourists. But the essential fact remains. In over 60 years since the first descent, fewer than 30 people have been there. The bottom of our own planet, the lowest point on the surface of the world we live on, is less visited than the moon. Here is something that surprises almost everyone who hears it for the first time. The deep ocean is not silent. We tend to think of it that way. A vast, dark, quiet void. And in terms of what a human ear could detect, it is. At the bottom of the Mariana Trench, you would hear nothing. Your eardrums would not function at that pressure, but the ocean is full of sound. And hydrophones, underwater microphones, some placed by the military during the Cold War and later made available to scientists, have been recording that sound for decades. Whale songs. Blue whales produce calls that are among the loudest sounds made by any living animal, up to 188 decibels. These low-frequency moans can travel thousands of kilometers through the deep sound channel, a layer of the ocean at roughly 1,000 meters depth, where the speed of sound reaches a minimum, causing sound waves to refract inward and travel enormous distances without losing energy. A blue whale calling in the mid-Atlantic can, in principle, be heard by a hydrophone in the Caribbean. The ocean is an acoustic highway, but some of the sounds recorded in the deep ocean have no known source. In 1997, NOAA's Equatorial Pacific Ocean Autonomous Hydrophone Array recorded an ultra-low-frequency sound of enormous amplitude. It rose in frequency over about 1 minute, was detected by sensors more than 5,000 kilometers apart, and then stopped. They called it the bloop. For years, the bloop was the subject of speculation. Its profile did not match any known geological, mechanical, or atmospheric source. Its amplitude suggested something enormous, far larger than any known animal. Some popular accounts linked it to undiscovered deep-sea creatures. Others, inevitably, to sea monsters. NOAA eventually attributed the bloop to an ice quake, the cracking and fracturing of a large iceberg. The frequency profile and geographic origin are consistent with ice events in the Antarctic. That explanation is now widely accepted. But the bloop was not the only unexplained sound. The upsweep, first detected in 1991 and recorded consistently since. A narrowband sound that rises in frequency over several seconds, repeating regularly. It appears to be seasonal, strongest in spring and autumn. After more than 30 years, its source has not been definitively identified. The leading hypothesis is volcanic, underwater lava interacting with seawater, but it has not been confirmed. The slow down. Recorded in 1997, the same year as the bloop, a sound that gradually decreased in frequency over about 7 minutes. Detected across the entire Pacific basin. Tentatively attributed to ice friction, an iceberg dragging along the seafloor, but never conclusively sourced. Julia. A strange, wailing sound lasting about 15 seconds, recorded in 1999. Also attributed to ice and the 52 Hz whale. Not a single recording, but a recurring signal detected since 1989, a whale call at a frequency of 52 Hz, significantly higher than any known species. Blue whale calls are typically 10 to 39 Hz. Fin whales call at about 20 Hz. This one calls at 52. It has been tracked migrating across the Pacific alone for over 30 years. No other whale has ever been recorded calling at this frequency. It has been called the loneliest whale in the world. Whether it can hear or be heard by other whales is unknown. Whether it is a hybrid, a malformed individual, or simply an outlier is unknown. It has never been visually identified. Somewhere in the Pacific Ocean, a whale has been calling at a frequency that no other whale uses for at least 35 years, and nobody has ever seen it. The deep ocean is not silent. It is full of voices. Some of them we recognize. Some of them we have explained. And some of them we have been listening to for decades without knowing what they are. Part 3. What we do not know. There is something deeply wrong about a species that can find microplastics at the bottom of the Mariana Trench before it can find most of the organisms that live there. In 2019, a newly described species of amphipod, a small crustacean found in the Hadal zone, was named Eurythanes plasticus, not because of its appearance, not because of its habitat, because researchers found microplastics inside its body. They named it after its own contamination. That amphipod had never been seen by science before. Its first contact with humanity was through the pollution that reached it before the scientists did. Microplastics have now been found in sediment cores from every ocean trench tested. In the Mariana Trench, in the Kermadec Trench, in the Japan Trench. Tiny fragments of synthetic material, clothing fibers, packaging, broken down bottles, settling through the water column for months or years, arriving at depths where nothing else from the surface world ever reaches. And it is not just plastic. Persistent organic pollutants, PCBs which were banned decades ago, have been found in the fat tissue of Hadal amphipods at concentrations higher than in some of the most polluted rivers on Earth. These chemicals do not biodegrade. They do not dissolve. They accumulate, passing from organism to organism, concentrating as they move up the food chain. The deep ocean, the most remote environment on the planet, is not remote enough to be clean. But pollution is the problem we at least understand. The one that may cause more irreversible damage is something most people have not heard of: deep sea mining. The abyssal plain is scattered with polymetallic nodules, potato-sized lumps of manganese, nickel, cobalt, and copper that formed over millions of years on the seafloor. These metals are critical for modern technology: batteries, electric vehicles, electronics, renewable energy infrastructure. And the nodules sit on the surface, unburied, in what mining companies describe as a simple collection operation. The International Seabed Authority, a United Nations body, has been issuing exploration contracts for years. Several companies are now in the advanced stages of planning commercial extraction. The technology exists. The economics are being tested. The regulatory framework is being debated. And the science says, we do not know what we would destroy. The nodules are not just rocks. They are habitat, organisms attached to them. Microbial communities live on and inside them. The sediment around them hosts a web of life that is adapted to conditions that have remained stable for millions of years. A single pass of a mining collector, as essentially a giant vacuum cleaner dragged across the seabed, would remove the nodules, destroy the organisms attached to them, and create a plume of resuspended sediment that could spread for hundreds of kilometers. Recovery times for abyssal ecosystems are measured not in decades, but in centuries, if recovery happens at all. Some researchers believe the damage would be functionally permanent on any human timescale. And here is the part that makes this different from most environmental stories. With deforestation, we at least know what we are cutting down. We have catalogued the trees. We have studied the species. The loss is measurable because the baseline is known. In the deep ocean, we do not have the baseline. We do not know what lives there. We have not catalogued the species. We cannot measure what we are about to lose because we have not finished finding it. We would be destroying things we have not discovered yet. That is not a metaphor. That is the literal situation. NOAA estimates that millions of species in the ocean have not yet been described by science. Not thousands, millions. That number is hard to sit with. We live on a planet where we have named every continent, mapped every mountain range, and photographed every coastline from orbit. And yet the majority of species in the largest habitat on Earth have never been seen, named, or studied. Every single deep-sea expedition that uses remotely operated vehicles or crewed submersibles to explore a new area of seafloor reports, encountering organisms that cannot be matched to any known species. Not occasionally, routinely. On the 2026 Cook Islands ROV exploration, happening right now as I write this, NOAA is conducting live dives to explore deep-sea habitats of the Cook Islands in the Pacific. The dives are streamed live. Viewers watch in real time as cameras descend into waters that have never been observed before. And in virtually every dive, something appears on screen that the onboard scientists cannot immediately identify. This is not a function of bad taxonomy or insufficient databases. It is a function of the size of the unknown. The deep ocean is so vast, so varied, and so poorly sampled that novelty is the default, not the exception. And it is not only new species, it is new ecosystems, new relationships, new forms of biology that expand what we thought was possible. In 2023, researchers discovered a hydrothermal system beneath the Arctic Ocean that was unlike any previously known. The chemistry was different. The organisms were different. The energy pathways were different. It was, in biological terms, a new world, existing on the same planet, in the same ocean, and entirely unknown until someone looked. How many more are there? We genuinely do not know. And that uncertainty is not a failure of science. It is a measure of how large the ocean is, how deep it goes, and how recently we started looking at it seriously. Consider this comparison. The total area of the deep ocean floor is approximately 360 million square kilometers. The total area directly observed by human eyes or cameras is, by NOAA's own estimate, an area roughly equivalent to Rhode Island, about 4,000 square kilometers. That means, for every square kilometer of deep ocean floor we have actually looked at, there are roughly 90,000 square kilometers we have not. 90,000 to 1. That is the ratio of the unknown to the known on our own planet. So if the deep ocean is the largest unknown on Earth, if it covers more area than every continent combined, if it contains millions of undiscovered species, if it harbors ecosystems we have not imagined, then why are we not exploring it? The answer is money and politics, and a failure of imagination so complete it would be funny if it were not so expensive. NASA's annual budget is approximately $25 billion. That funds Mars rovers, space telescopes, the Artemis program to return humans to the moon, and the entire apparatus of planetary exploration. NOAA's ocean exploration budget, the part specifically dedicated to exploring the deep ocean, is roughly $40 million a year. Read those numbers again. $25 billion for space, $40 million for the ocean. That is a ratio of roughly 600 to 1. For every dollar spent looking outward into space, less than 0.2 of a cent is spent looking downward into the ocean. And the ocean is right here. It covers 70% of the surface of the planet we actually live on. And we fund its exploration at a fraction of what we spend searching for water on Mars. Water that, if it exists, would be far less accessible than the water above the hydrothermal vents at the bottom of the Atlantic. This is not an argument against space exploration. Space exploration is valuable, important, and has produced discoveries that changed human civilization. It is an observation that the funding disparity is so extreme that it requires an explanation. The explanation is straightforward, but unflattering. Space is exciting. The deep ocean is not, or at least, it does not look exciting in budget hearings. A photograph of Mars generates congressional support. A photograph of abyssal mud does not, and there is a structural problem. Ocean exploration does not have a single unifying goal equivalent to landing on the moon or putting humans on Mars. There is no finish line, no flag to plant, no moment that makes the evening news in a way that justifies next year's budget. It is incremental, unglamorous, and the creatures you discover do not look good on a poster. The result is that the most biologically rich, least explored, most scientifically productive environment on Earth receives funding that would not cover the cost of a single Mars helicopter. And that is a choice, not an inevitability. A choice, which is ironic, because the strongest argument for exploring the deep ocean is, in fact, space. Beneath the ice crust of Jupiter's moon Europa, there is almost certainly a liquid water ocean, not a small one. Europa's ocean is estimated to contain roughly twice the volume of all Earth's oceans combined. It is kept liquid by tidal heating, the gravitational flexing of Europa by Jupiter's enormous mass, which generates enough internal heat to maintain liquid water despite surface temperatures of minus 160 degrees Celsius. We cannot see that ocean directly. The ice crust is estimated to be 10 to 30 kilometers thick, but the evidence for liquid water beneath it is strong. Plumes of water vapor have been detected erupting through cracks in the ice, and the surface shows patterns of fracturing and refreezing consistent with a shifting liquid layer below. Now ask yourself, if there is life in Europa's ocean, what would it look like? What would it eat? How would it survive without sunlight, at enormous pressure, in total darkness? The answer to every one of those questions already exists on Earth, at the bottom of our own ocean. Chemosynthetic bacteria at hydrothermal vents showed that life does not need sunlight. The deep biosphere showed that life can persist in rock for 100 million years. Extremophiles showed that life can handle pressure, heat, cold, and acidity far beyond what was thought survivable. Every discovery at the bottom of our ocean has expanded the range of conditions under which life is possible. And every expansion of that range has made life on other worlds more plausible, not less. Saturn's moon Enceladus is even more compelling. It is smaller than Europa, but its geysers are more dramatic. Enormous plumes of water vapor and ice particles erupting from the South Polar region, shooting hundreds of kilometers into space. The Cassini spacecraft flew through those plumes and detected molecular hydrogen, a potential food source for chemosynthetic microorganisms, along with organic molecules. That is not proof of life, but it is a menu. Liquid water, chemical energy, organic compounds. The same ingredients that sustain life at the bottom of our ocean. And here is the part that matters for this video. If you want to know what life on Europa or Enceladus might look like, how it might function, what it might eat, how it might survive, you do not need to go to Jupiter. You need to go to the bottom of the Pacific. The analog is already here. We just have not finished studying it. The deep ocean is not just the last unknown frontier on Earth. It is the dress rehearsal for finding life beyond it. Let us go back up. Start at the bottom. Challenger Deep. 10,984 meters. Pressure of 1,100 atmospheres. Temperature barely above freezing. Total darkness. Microplastics in the sediment. Foraminifera in the mud. The silence of a world that has never known sunlight. Rise. Pass through the Hadal zone. The trenches narrow. The walls steepen. Amphipods the size of your hand swarming on bait that fell from 2 miles above. The snailfish, translucent, delicate, living at pressures that crushed a purpose-built robot. Every expedition finds something new. Every single one. Rise. The abyssal plain. 4,000 meters. The largest habitat on Earth. Flat, silty, monotonous to the untrained eye. but beneath it, in the rock itself, the deep biosphere. Organisms so old they have not divided since the dinosaurs were alive, and at the hydrothermal vents, ecosystems that owe nothing to the sun. Tube worms with no mouths, shrimp that navigate gradients between near-freezing water and superheated fluid, chemistry instead of sunlight, life that rewrote the textbooks in 1977 and has not stopped rewriting them since. Rise, the midnight zone, total darkness, but not total emptiness. The anglerfish with its dissolving males, the giant squid with eyes the size of dinner plates, watching for the bioluminescent wake of sperm whales, marine snow drifting down, the only connection between the world of light and the world without it. Thin, fragile, the thread everything depends on. Rise, the twilight zone. The light begins to return, faint blue filtered through hundreds of meters of water, and suddenly life explodes. The deep scattering layer, the wall of biomass that fooled World War II sonar operators into thinking they had found the seafloor. Billions of organisms rising every night to feed, sinking every morning to hide. The largest migration on Earth, happening in darkness, invisible from the surface. Hatchetfish with belly lights that erase their silhouettes. Glass squids so transparent you can see through them. Siphonophores, colonies pretending to be individuals, stretching tens of meters through the blue. Rise, the sunlight zone, warmth, color. The first photons that have come all the way from the sun without being absorbed. Phytoplankton, billions of them, producing half of every breath you will ever take. The coral reefs, the dolphins, the sharks, the whales, the world you recognize. The thin, bright skin stretched over an ocean you now know is mostly darkness. Break the surface. Feel the air. And look down. It is all still there. Right now. Beneath you. Beneath every ship, every swimmer, every grain of sand on every beach. The zones. The creatures, the vents, the trenches, the sounds. The things we have named and the things we have not. 70% of this planet. Less than 0.001% explored, and you just went all the way to the bottom and back. If you are still here, and I know that is a lot to ask at the end of 3 hours, then you now know something that most people on Earth do not. You know what is actually down there. Not the cartoon version, not the documentary highlight reel, the real picture, with its extremophils and its plastic bags and its unexplained sounds and its species named after their own contamination. And you know the number, 0.001%. That is how much we have seen. Which means everything in this video, every creature, every vent, every trench, every discovery I described, came from a sample so small it would not be statistically significant in any other field of science. We drew all of these conclusions from less than 1/10,000th of the data. Imagine what the other 99.999% contains. The most alien world ever discovered is not in space. It is right here, beneath us, right now, in the dark, and we have barely looked. Follow MindSnap. Facts that change how you see everything.